deals with the reactions, chemical reactions, and the whether you are getting electric current or you are consuming electric current. Okay, electrolytic cell, non-spontaneous reaction. So what's the delta G value for the electrolytic cell? Can you tell me? Delta G value, is it going to be positive or negative? Tell me. So delta G is going to be non-spontaneous reaction, means electrolytic cell contain those reactions which cannot happen on their own. Okay, so it is a non-spontaneous reaction, and this delta G is going to be positive. If this is positive, you need to put work, you need to pass electric current. Okay. On the other hand, galvanic cell or the electrochemical cell is used to generate electric current, right? And this is the convention that already you know, as you told me. Okay. And this is salt bridge. So salt bridge should contain ions which should have equal velocity constant. They need to move, the cation and anion need to move with this equal speed. What's the purpose of the salt bridge? Any idea why we use salt bridge? So salt bridge is used to maintain the electrical neutrality of the cell. Okay, it maintains the overall neutrality such that the cell, in this case you will have the zinc ions accumulating, and in this case you have the sulfate ions accumulating. So the salt bridge brings in the oppositely charged ions on both the sides to maintain the electrical neutrality. Okay, and there is an EMF which is associated. Any idea what's the EMF of this zinc and copper sulfate, standard EMF value of this? Yeah. What's the EMF value of this? It is 1.1 volt. Okay, this is the standard EMF under standard condition. Okay, so these are the representation of the cell. And how do you measure the electrode potential? Any idea? Yeah, Hanifa. Electrode potential is the it is the potential of the individual electrode. When you take the difference, you get the EMF of the cell. Okay, EMF of the cell is E right minus E left in terms of standard reduction potential. Okay, so it is the electrode potential when you have standard. If you have standard value, it means the concentration of the zinc sulfate is 1 molar, copper sulfate is 1 molar, and 298 Kelvin, and the pressure is 1 bar. Okay, but so if you take the difference of the standard potentials, you get the EMF of the cell, that you know already, right? And but how to measure the electrode potential of individual electrode? That is by standard hydrogen electrode. Okay, standard hydrogen electrode under standard condition, its electrode potential is taken as 0, right? It's 0, and every electrode is connected to it. Okay, so let's do some questions. Yeah, so what's going to be the answer to this one? Tell me. Yeah, Nifa. Reduction potential of any half cell is measured against what? Just the basic definition, that's it. It is What? So how do you measure the electrode potential of a single electrode? Okay, only just one electrode if you put. And so how you will get the electrode potential of that single electrode? Okay, that is with respect to what? Any idea? Is it the zinc half cell, the hydrogen half cell, copper half cell, or hydrogen half cell? Hydrogen half cell is written over here, but it is showing different concentrations. Okay, so one is 1 molar and another, as you can see over here, is 10 to the power minus 7 molar. So now the question is, which is going
hydrogen one with the 1 molar.
Yeah, hydrogen 1 molar. Yeah, this is the standard electrode, standard hydrogen electrode. And what's the what its value for the standard reduction potential is? Its value is taken as 0. Okay, right? So its value is taken as 0. And but this is not the standard value. Okay, this is not standard because the concentration need to be, the pressure of the hydrogen gas should be 1 bar. That also you should know. If the hydrogen pressure is changed, then also it is not standard. And the temperature should be 298 Kelvin. If the temperature changes, then also it is not standard. So all the three things, the concentration, pressure, and the temperature come under standard condition, right? So what you do, you suppose if you want to measure the electrode potential of copper, so you take a copper electrode. This is on the right hand side under a standard condition. You take the standard hydrogen electrode under standard condition, as you can see over here. You connect them, okay, and you measure the voltage. Okay, you connect them, you measure the voltage, and this voltage is 0.34 rounded off. Okay, value. So this voltage is E right minus E left. Okay, 0.34 equal to electrode potential of cathode minus electrode standard reduction potential of anode. Both you should take in reduction potentials. Okay, because standard reduction potential, though you can work with the standard oxidation potential also, but standard reduction potential is actually the most better way. It is the, as per IUPAC convention, the standard reduction potential is taken as the standard electrode. So this is the overall voltage or the EMF of the cell. This is for the copper, we don't know its standard value. For hydrogen, actually, it is assumed to be 0 volt. So you put 0 volt here, so you will get for the copper. So you connect the copper, okay, and each electrode with each standard hydrogen electrode one by one, and you get the value of electrode potential of each electrode by connecting it one by one to standard hydrogen electrode. Okay, similarly zinc is, copper is 0.34, zinc is minus 0.76. Okay, and there are two types of electrode potential. One is oxidation potential and another is reduction potential. So here you can see this is reduction potential. It is known as SRP, standard reduction potential. Okay, which tells us the electron accepting tendencies of zinc. And this is, zinc is getting oxidized by losing electron. This is known as SOP, standard oxidation potential, where zinc is losing electrons. Okay, so for an element, metals generally give electrons. Okay, so metals have a tendency, metals are electropositive, the tendency to lose electron. So when you show them losing electron, this is a standard oxidation potential, and that for metals it is going to be positive, except for few metals, copper, silver, and gold, right? For other metals it is going to be positive. Okay, but if you show the reverse, in which the metal ion is accepting electrons, that is standard reduction potential, SRP. Okay, So metals don't want to accept electron, that's going to be negative value, minus 0.76. Okay, so oxidation potential of an electrode and reduction potential of an electrode both have equal magnitude but opposite sign. And but IUPAC, as I told you just now, standard reduction potential is taken as the standard electrode potential. Okay, right? So we arrange all these value, and what we get an electrochemical series. Electrochemical series you can see over here. Okay, so first questions, most of the questions come for the electrochemical series. Look here, this is zero value. Okay, the one who are at the top, will have positive value, means these metal ions or the elements have more tendency to accept electron, and one who are below hydrogen will have negative reduction potential. So these have negative reduction potential, means they don't want to accept electrons, right? Means these are mostly metals, but not all metals. Okay, so this is the electrochemical series. So tell me, who is the strongest oxidizing agent if you have this electrochemical series? So which is the strongest oxidizing agent? Any idea?
Fluorine.
Yeah, fluorine is the strongest oxidizing agent because it has maximum tendency to accept electron. Its standard reduction potential is maximum. And who is the strongest reducing agent?
Hydrogen.
No. Yeah, which one?
Hydrogen.
It is lithium. Okay, so look here. So lithium doesn't want to accept electron. This is one electron. Okay, so lithium, if it accepts electron, and you will have negative value. Negative value means it doesn't want, Li plus doesn't want to accept electrons. That's why it is having negative value. Okay, but if you reverse the equation will become like this: Li giving Li plus and losing one electron. Okay, but if you reverse the equation, the value will, or sign will also get reversed. This is standard oxidation potential, where Li is changing to Li plus, that is plus 3.04 volt. That is very high positive value. So high positive value means it has a tendency to lose electrons. Okay, and means the lithium is the strongest reducing agent. Is it clear, Hanifa? F2 is the strongest oxidizing agent and lithium is the strongest reducing agent. Okay, so the first application of electrochemical series is prediction of oxidizing and reducing agents, which can reduce, who can accept electron, and who can oxidize others. Okay, so let's do one question. So what's going to be the answer to this one?
Zinc, the first one.
A standard reduction potential of the following, yeah, strongest reducing agent. Yeah, the answer is going to be, yeah, zinc doesn't want to accept electron. Its value is very negative, means it's want to lose electrons, right? So zinc is the
Yes.
right answer. Correct. Okay, yeah. And what about this one? So what's going to be the answer? Iron is accepting electron, and its electron accepting tendency is shown by its Standard reduction potential minus 0.44. And zinc cation is accepting electron and its electron accepting tendency is minus 0.76. Though the negative value for both of them makes clear that both do not want to accept electrons. Okay. But the question is something else. Question is not asking whether they want to accept electrons or not. They are asking something different. So what's going to be the answer?
C.
C or B? Answer is going to be option A. Okay. Zinc is more electropositive because it doesn't want to accept electron. Look here. That's why its value is so negative. But if it doesn't want to accept electrons, means what? It can lose electrons. If you do the reverse, it will have high positive value. Means zinc can lose electrons. Zinc is more electropositive. Okay. Is it clear? Clear?
Yes.
Right? Okay. So let me ask one more
Yes.
question. This is cobalt, lead, and cerium. Ce3 plus. Their E0 values are plus 1.81, plus 1.67, plus 1.61 volt. And there is bismuth also. Bi3 plus, accepting 3 electrons to give you bismuth. Its value is plus 0.20. Okay. So what is the correct order of oxidizing power? Increasing, oxidizing power, and tell me what's going to be the right answer. What's going to be the increasing
The
oxidation?
fourth one.
Which one?
The last one, fourth.
Last one. So the increasing oxidizing power, right? It is going to be the maximum for cobalt 3 plus, because it can accept electron by maximum extent. It has maximum tendency to accept electrons. That's why it is having maximum. So it is itself getting reduced, and it can bring the oxidation of others. Right? Correct. So oxidizing power is increasing. Correct. Very correct. Okay. So other application of the electrochemical series is to calculation of standard EMF of the cell. Okay, you can calculate the standard EMF of the cell by taking the difference of reduction potential of cathode and anode. Okay, but that is only under standard condition. The other thing is, if the EMF comes out to be positive, you can also predict whether the cell is going to work or not. If the EMF comes out to be positive, the cell is going to work and it is going to be spontaneous. But the EMF comes out to be negative, the cell is not going to work. It will not work. Okay. So let's do this question. Yeah, okay. Tell me what's going to be the answer. Yeah, Nivra. So standard electric potential for 10 is 0.15, copper is minus 0.74. Okay.
Yes, sir.
So tell me what's going to be the EMF of the cell. Cell potential means, so these are for the individual electrodes. Okay. So what's going to be the EMF of the complete cell? Right?
0.89.
Which one?
A.
A, option A. Okay. So the reduction potential of the cathode. So who will act as a cathode? The one who is having larger value, right? Plus 0.15. Okay, this is having larger value because this is less than 0, negative. Minus, and you need to put it with the sign. Okay. So it is 0.89 volts, right? Very correct. Okay, clear? Yeah, let's do this. Yeah, tell me what's going to be the answer. Yeah, Nifa. So this equation is already given to you, right?
Yes.
This equation, in this equation, you need to determine who is cathode, who is anode. Okay, and this is actually this is the final cell equation. But if the equation is not given, you will yourself decide. Like in the above question, you yourself decided what was cathode and what was anode. Okay, but in this case, the equation is already given to you. So as per the equation, you need to decide who is cathode, who is anode. So Mn, you can see here, this Mn plus 3 is on the right hand side. Okay, it is forming. Right hand side means it is forming. So this second equation is giving Mn3 plus. Okay, right? So this second
Yes, sir.
equation is acting like it is in this, it is written as it is accepting, but it is losing. Mn2 plus is losing electron in this. That's why it is forming Mn3 plus. So this is acting as anode, right? Clear? Is it clear? Because suppose if Mn3 plus is on the left hand side of the equation, on this side, that means it is acting as a cathode. It is getting reduced, but it is not getting reduced. Actually, it is forming. It is forming. How it is forming? It is happening in this way. Clear?
Sir.
So it means what? It means the Mn3 plus is forming, Mn2 plus is losing electrons, and so wherever the loss is taking place, that is cathode, that is anode oxidation, right? Loss of electron. Okay, so this is anode and this is cathode. And when you write the overall cell equation, you make how you calculate. So if the nothing is given, you will yourself decide your cathode anode equation. But in the equation, cathode anode are these. So EMF of the cell will be equal to E naught cathode in terms of reduction potential. E naught anode. Okay. So for cathode, it is minus 0, minus 1.18. This one. And for anode, it is minus 1.51. Right? So overall, it is going to be how much? What's going to be the answer now? Tell me. Yeah. Yeah, Nifa, tell me quickly. What's going to be the answer? Minus,
269.
yeah, minus
69.
2.69 volt, right? So for this equation, okay, this is the EMF of the cell. So is the cell going to work or not? Tell me. If the EMF comes out to be negative, what does this indicate?
I don't know.
Yeah, the cell is not going to work, right? The reaction will not occur. It is non-spontaneous, right? So this means it will not work. I will. So this is A is going to be the answer. Clear,
Yes.
right? So yeah, let's do this. Yeah. So reduction potential is given for tin and iron, and the cell equation is given. Yeah. So what's going to be the answer? Who is cathode? Who is the anode in this? Look at the equation. Tell me. So one who is getting reduced is cathode. So who is getting reduced? Iron is getting reduced, right? It is accepting electron.
Yes.
Okay, this is cathode. This is cathode. As per the equation. And tin is getting oxidized. This is anode. Okay, this is for the cathode. This is for the anode. Okay, so standard EMF of the cell is E cathode, okay, minus EL, right? So minus 0.44 minus of minus 0.14. We need to take care of the sign. Okay, this is going to become positive. So minus 0.44 plus 0.14. Okay, so it is going to be minus 0.301. So here also this reaction is not going to happen. Okay, if I ask you, is the tin going to reduce the iron, or is the iron going to reduce the tin? Okay, in this case, it is shown that the tin is reducing iron. That is not going to happen. Okay, because the EMF is minus 0.30. If the EMF comes out to be negative, means the reaction is not going to happen. Clear? So iron can reduce tin. Right? Okay. So the next application of the electrochemical series is, so we have hydrogen as a standard electron. And another application is whether to predict metal is going to liberate H2 gas. There are certain, from the acids, there are certain metals where you put the metal into acid, right? Hydrogen gas comes out. And there are uh, certain metals which do not give hydrogen. Okay. So any idea how you determine it? So the answer is this is the electrochemical series. Okay. So suppose if I write for silver, okay, silver want to accept electron more than the H plus. Why silver want to accept electron more than the H plus? Because silver is having higher positive value as compared to H plus, which is 0 volt. Okay, so can you expect the silver when you put it in hydrochloric acid to lose electron to H plus? Answer is no, because silver has more higher tendency to accept electrons. So silver has a higher tendency to why it will lose. Okay, it will first gain electrons. It will not lose its electron to H plus. But if you take iron, or any other metal, which are most of the metals are below hydrogen, you will have negative value of SRP. It means that the iron doesn't have tendency to accept electron. Okay, it is negative. Hydrogen has some tendency which is 0. So 0 is larger, higher than negative term. So comparatively, hydrogen has more tendency to accept electron than the Fe2 plus. Is it clear? So if you put the iron in HCl, hydrogen being having higher standard reduction potential value, it can accept electron more readily, more easily from the iron. So iron is going to give electron to the H plus, and it is going to liberate H2 gas from the HCl. So I hope this is clear, right? Any doubts in this? Okay, so let's do some question. Yeah, and this is for the tin, this is for the copper. So which statement is correct? So who has more tendency to gain electrons? Is it the tin plus 2 or the copper plus 2? It's the copper plus 2, because it is having higher positive value for the reduction. Okay, 10 plus 2 has negative value, which is lower. So these are some multiple statements. So tell me what's going to be the answer. So copper ion can be reduced by hydrogen.
I'm not sure.
Hmm? Can copper ion be reduced by hydrogen? So can hydrogen give its electron to copper? So can copper take the electron from H2? The answer lies in the value, in electron accepting tendency, that is standard reduction potential. So for copper, it is having plus 0.34 volt. For hydrogen, it is having 0.0 volt plus. So if you compare both of them, the copper is having higher value for accepting electrons, higher tendency to accept electrons, right? So it will gain electrons, okay, from the hydrogen. It can It can accept electrons. Okay, this is actually normally metals do not do this. Metals actually have negative SRP value, but some metals have positive. Clear? So I hope this is clear. So copper ion can be reduced by hydrogen gas. This is true. Copper can be oxidized by H plus. Copper can oxidize by H plus if H plus can accept electrons from the copper. Then H plus can oxidize copper, but that cannot happen because it is having lower zero value and that one is having higher value, means copper is having higher tendency. If the copper is having higher tendency, that how can higher tendency to accept electrons? If it is having higher tendency to accept electrons, then how it can give its electron to H plus? So this is incorrect. So 10 plus 2 ion can be reduced by hydrogen. So 2H plus 2 electron, next one SN2 plus 2 electron SN. Okay. So 10 plus 2 ion can be reduced by hydrogen. Can 10 plus 2 take electrons from hydrogen? So hydrogen, the voltage is 0 volt, electrode potential. 10 is minus 0.14 volt. So can 10 having lower electron accepting tendency, lower value, can accept the electron from hydrogen which is having higher value, 0 is higher than minus 0.14? The answer is no, that also cannot happen. Okay, is it clear? Copper can be oxidized by 10. So copper can be oxidized by 10. Okay, let's check this. So this is having higher electron accepting tendency, copper to this. So copper, if it means to say that the copper is oxidized by 10 plus 2, means 10 plus 2 has taken the electron from the copper. That cannot happen because the 10 plus 2 is having lower value. Copper is already having higher electron accepting tendency. 10 is having lower electron accepting tendency. So how can 10 accept the electrons from the copper? Okay, can copper be oxidized by 10? No, that also cannot happen. Is it clear? Each option, you should do it in this way. Okay, these are the most common question in all the examination. You can understand slowly. You need to take time initially, but you know many things. Okay, but if there is a confusion, you can think in the way in which I am doing. Okay, clear? So next is Nernst equation. So when do we use Nernst equation? Tell me.
Find the electrode potential.
Yeah, it's electrode potential, but that electrode potential can also be found out by electrochemical series. Then why do we need to use this Nernst equation?
With respect
Yeah,
to
it is in the,
concentrations.
yeah, it is, you can find the standard value of EMF of the cell. Okay, standard EMF value you can find out, right? By using that electrochemical series. If you have non-standard condition, okay. Under non-standard condition means if the concentrations are changing, concentration not equal to 1 molar, temperature not equal to 298 Kelvin, pressure, if there is any gas, is not equal to 1 bar. These are non-standard conditions. So if you have non-standard condition, then you can use this, right? So it is the EMF of the cell, which is the non-standard. Look here, there is no E naught. This is the standard and this is the non-standard. Okay, so non-standard EMF equal to standard EMF of the cell. You can get this value from, this value can be obtained from the electrochemical series. Okay, and R is gas constant 8.314, temperature is in Kelvin. N is the number of electron transferred in the balanced chemical equation, and F is the charge of the 1 mole of electron, that is 96500 coulomb per mole, right? So yes, take E cell equal to E naught cell minus 0.0591 upon N log of reaction quotient. Okay, this is Q is the reaction quotient. Reaction quotient is exactly same as, it is exactly same as that of your equilibrium constant, but the difference is only that the equilibrium constant has only equilibrium concentration, but if you write the same expression and if you put the non-equilibrium concentration or the concentration which are given at that time, that is actually the, that is the reaction quotient, right? So this is the reaction quotient. So the concentration of each reactant, was concentration of each product raised to the power its coefficient of the balanced chemical, concentration of products raised to the power the their stoichiometric coefficient divided by concentration of reactant, each raised to the power its stoichiometric coefficient. Okay, so this is how you are going to measure it, right? Clear? So suppose if the concentrations are given to you, this is the overall cell equation. Standard EMF you can find out very easily, E cathode minus E anode. You can write the expression for the next equation. E cell equal to E naught cell minus RT by NF ln of reaction quotient, which include the concentration of products, each raised to the power stoichiometric coefficient, they are 1 divided by concentration of reactant. Okay, clear? So now this concentration of solid is not considered, it is constant, it is taken as 1. Only you will take the concentration of the ions, right? This is how you are going to do it. Clear? And if the overall EMF of the galvanic cell comes out to be negative, then what it implies? What can you say about the galvanic cell? Cell reaction. Yeah. Is the cell reaction can happen on its own? It's very easy. You know it very well. What's going to be the answer? Yeah, Nifa. The cell reaction, is it spontaneous or non-spontaneous? What's the answer?
B.
Yeah, correct, B. It's non-spontaneous, right? So exothermic and this is not correct, okay? Negative value means it's not going to work, right?
Oh,
Right? Any doubts? Any doubts in this? Would you like to add something? Yeah, okay. So this is the next question, or we can do some more. This is the standard EMF of the silver electrode. It's 0.8 volt. Okay. So what's the EMF of this electrode? What's the electrode potential? If you have taken 0.1 molar Ag plus concentration instead of 1 molar. Yeah, tell me. Here we need to apply nonce equation. Okay. It is because these are non-standard condition, and if any of the concentration is not 1 molar, temperature is not 298. If nothing is given, temperature take 298. Okay. Concentration is changed, pressure is not required because there is no gas involved. Right? So tell me what's going to be the value. Yeah, Nifa. So what are we going to write? We are going to write the nonce equation. All the constant, the values we have taken as 0.591, you can take it as 0.06 also. That's going to be easy. Into log of reaction quotient. The concentration of silver, but silver is solid, so you don't have to take the concentration. Take the concentration as 1. That's not going to change. Divided by the concentration of Ag plus. Right?
Yes.
So tell me what's going to be the value. Have you solved it? So what's the value of this? log 1 upon 0.1. 0.1 is 1 upon 10. Okay. So this is log 10. 1 upon 1 upon 10. 10 will go in the numerator. 0.06 minus 0.80. So log 10 is 1. Okay. So it will be equal to 0.80 minus 0.06. So it is going to be 0.74, right? Is it clear? So it's going to be less, right? So I hope this is clear to you. Okay, let's do this question, this one. So this is the overall cell equation. So here you don't have to write the Nernst equation, but orally you can do it. Tell me what's going to be the answer, how you are going to do it. Think in terms of equilibrium. In 11th, you may have studied equilibrium, right? And by looking at the equation, you can predict when the reaction is going to move in the forward direction, when the reaction is going to move in the backward direction. If the reaction is the tendency of the reaction to occur more in the forward direction is increased, okay, right? Then actually the EMF also increases, right? But if the tendency of the reaction to take place in the forward direction decreases, then the EMF also decreases. Okay. Right. So predict which change will decrease the cell voltage. The change which is going to take the reaction in the backward direction is going to decrease the cell voltage. Yeah, tell me.
One.
Decrease in Ag plus. Yeah, one is also correct. You are very right. If you decrease the Ag plus concentration, the reaction is not going to move forward because you are decreasing the reactant. Reaction is going to move backward. And it is going to decrease the EMF of the cell. Increase in Fe3 plus, if you increase product, the reaction will start happening in the backward direction. Okay. So if you increase the product, that also can happen, right? Because your product you are increasing, will go back. If you are decreasing the reactant, then also it is going back. Okay. So, but increase or decrease in amount is not, it will not affect, because in equilibrium, you write only the concentration of ions. Okay. You don't write the concentration of solid. We have taken the concentration of solid as as 1. Okay, you must have seen, right? So this is not going to change. Okay, so which of the following steps will pull the reaction in the backward direction? So it is the first and the second one. Is it clear? Right?